You ever stop and think about the incredible engineering that's completely hidden, right in plain sight? Well, today we're pulling back the curtain on one of those really fundamental processes, pump sizing. Now, it might not sound super glamorous, but trust me, it's the invisible force that keeps our world running.
I want you to picture any large industrial facility, a water treatment plant, a refinery, you name it. They're kind of like these complex, sprawling cities. And all those thousands of meters of pipes you see, those are the highways, carrying essential fluids, water, fuel, chemicals, from one place to another, 24/7. So you gotta ask, right? With all that fluid traffic, how do you pick the perfect engine to keep it all moving? Because if you choose one that's too weak, well, nothing flows. And if it's too powerful, you're just wasting massive amounts of energy and you could even damage the whole system. Nailing that balance, that's the critical engineering challenge.
Okay, so to really get how they crack this problem, we're going to follow an engineer on a classic mission. The goal seems simple enough. Just move a certain amount of water from a source to a destination. But as you're about to see, the devil is always in the details.
And here's our map for the mission. We've got a reservoir over on the left, and our target is the tank on the right. So what's the catch? Well, the tank is 30 meters higher. That's about the height of a 10-story building, and it's a total of 41 meters away through a whole network of pipes.
The second you try to move that water, you're not just pumping a liquid. Nope, you are starting a battle with the fundamental laws of physics. Every single pipe, every bend, every valve, it all fights back. It creates resistance.
And engineers have a name for this total resistance. They call it system head. You can think of it as the exact amount of push or pressure the pump needs to generate to win that battle and get the water where it needs to go. It's the number that tells you exactly how tough the job is.
Now, this system head is really made up of two main opponents. First, you've got static head. That's just the raw fight against gravity, the energy you need just to lift the water 30 meters straight up. The second opponent is friction, which is caused by the water rubbing against the inside of all those pipes and fittings.
And here's where it gets really interesting. See, friction isn't some constant enemy, it's dynamic. The faster you try to push the water through the pipes, the harder friction pushes back against you. So that pressure you need, the system head, it actually changes depending on how fast you want the water to flow. So, with this moving target of resistance, how on earth do engineers find a pump that can perfectly match it? They can't just guess, they have to find that sweet spot, that one point where what the pump can do perfectly meets what the system needs.
Okay, this graph, this is where it all comes together. First, take a look at that orange line climbing upwards. That's our system curve. You can see that as the flow rate along the bottom increases, the total resistance, or head, on the left side goes up. This is basically the system's demand curve.
And pushing back against that demand is the blue line, the pump curve. This curve comes from the pump manufacturer, and it basically shows you the pump's personality. At low flow rates, it can generate a lot of pressure, but as you ask it to pump more and more water, its ability to create that pressure drops off. This is the pump's supply curve.
And right there, that is the aha moment. Where those two curves cross is called the operating point. It is the only point where the system is stable. It's the natural equilibrium where the pressure the pump can supply perfectly matches the pressure the system needs for that exact flow rate. Finding this one point is the entire goal.
You know, back in the day, finding that point involved all these tedious, super complex manual calculations. But today, engineers have a much more powerful tool. They can basically build the entire system on a computer before a single piece of steel is ever ordered.
They create what's called a digital twin, which is just an exact virtual replica of the physical system. This digital proving ground lets them test everything, run all kinds of what-if scenarios, and find that perfect operating point with incredible accuracy, all without any of the real-world risk.
And this is what that looks like. Using powerful open-source software like DWSIM, engineers can build a complete flow sheet. You can see every single piece from our problem right here. The reservoir on the left, all the pipe segments, the pump sitting in the middle, and the final tank on the right.
The level of detail they put in here is just incredible. The engineer inputs everything. The exact length and diameter of the pipes, what they're made of, in this case carbon steel, all the elevation changes, and even the expected efficiency of the pump itself. Literally, every single variable is accounted for. So, after building this digital twin and plugging in all the data, the engineer just hits solve. The software runs all the complex physics calculations in seconds and just spits out the final blueprint.
the exact numbers needed to go and build this thing in the real world.
And here they are, the key results. Now, the simulation gives you a really detailed report, but these 3 values, these are the most critical pieces of the puzzle. They tell the engineer everything they need to know to pick out the right equipment for the job.
First up, 2.06 kilowatts. This isn't just some abstract number, this is a real-world cost. It's the amount of electrical power that's required to run the pump all day, every day. That translates directly to the energy bill and the long-term cost of operating the system.
Next is this thing called NPSH, or Net Positive Suction Head. This one is a super important safety check. So think about how water boils at a lower temperature when you're on a high mountain, right? Well, a pump's inlet is a really low-pressure zone. And if that pressure drops too much, the water can actually start to boil and form vapor bubbles, even at room temperature. When these bubbles collapse, a process called cavitation, it's like tiny little explosions that can shred a pump from the inside out. So this NPSH value is a critical safety margin to make sure that pump has a long, healthy life.
So yeah, as process engineer Viraj Desai puts it in the article we're looking at, the whole process really just boils down to this: figuring out the required power of a pump so it can precisely overcome the system's total resistance, or its system head.
And we've only looked at one simple example here. But this exact same process, this digital calculation, is being done millions of times by engineers all over the planet. It's what makes sure our cities get water, that fuel gets to the gas station, and that our power plants can operate safely.
It is, truly, the hidden engineering that keeps our entire modern world flowing, quietly and efficiently, right behind the scenes.
So, the next time you turn on a tap, you'll know a little bit more about the incredible journey that water took just to get to you. And that leaves us with a final thought. What other invisible engineering calculations do you think are constantly running the world just out of our sight?